Hello, I'm Doug, and this is a talk I am going to present at the 8th International Conference on Clifford Algebras in Campinas, Brazil. Clifford Algebras are a type of math that try to extend these things known as quaternions, and this conference is focused on Clifford Algebras and their friends and buddies and their applications to physics. So hopefully this particular talk is very relevant because the title is New Quaternion Math Leads to New Reasons Why Physics Works. I will be presenting 3 new quaternion math widgets. The first is a new quaternion derivative that justifies the difference between classical and quantum physics. Now, that might be able to finally settle this debate between Einstein and Bohr, but also people will probably continue to fight over it. A second thing we introduce is new software that animates arbitrary quaternion functions. And I look at what U1, the symmetries U1, SU2, and SU3 look like, which are the symmetries that go into the standard model, which is the way that physics looks at the fundamental forces that work in the universe. That would be electromagnetism, the weak force, and the strong force, and I can even provide a picture of what gravity might be about. And the third bit of math is a commuting 4D division algebra that, together with the standard sort of quaternion, might be able to do the work of both gravity and electromagnetism. My background in doing physics is at the website quaternions.com. And the thesis there is that physics is the study of patterns of events in space-time using quaternions up to an isomorphism. Now, why did I put that in italics? Well, because most of physics works just fine without quaternions. We're doing the same thing exactly. I use quaternion notation, other people use scalars and vectors. And that's a perfectly fine way to do things. But if you want to do new physics, I think it's required that you actually do new quaternion math. In some ways, this is why we put so many research dollars into works on strings, because they are doing new math, and so it's easy to think that they are therefore doing new physics. Since they have their units for space completely and utterly wrong, it's not 9 dimensions, it's not 10 dimensions, I don't think there is any physics content in the entire body of work. That's rather harsh, but that's the way nature is. Nature is logically quite harsh. It's hard to do new things with quaternions. And that's why many people don't kind of work with them. I mean, there's so much one could play around with in strings, but with quaternions, it looks like, they're over 150 years old. How are you going to be able to do anything new with them? So if you do find something, it might just be important. So the first math problem is how to define a derivative of a quaternion function on a quaternion manifold. And if we look at the standard definition of a derivative and we simply apply it to the case of quaternions, then what we notice is that if we write the differential element on the left, it's not the same as writing the differential element on the right. And you could decide to work with left and right-hand derivatives, and Futur actually does that, and Sudbury actually formalizes it a little bit more. But it has a very serious problem, and that is that a function as simple as q squared is not analytic in Q. And that really limits its utility because once you have the polynomials, you basically have everything. You just build them out, other transcendental functions out of polynomials, and you'll be able to show they're analytic. But if you can't show q squared is analytic, you can't go anywhere. And to me, that's a fundamental problem, and why one should stay clear of just taking this straight out of a simple calculus book. So my solution to this issue is to use two limits in order to get a directional derivative along the real axis. This is kind of stealing from L'Hospital's rule, and L'Hospital actually stole it from a Bernoulli brother. But you have these two limits, and you let the three-vector part, the part that causes problems, go to 0 first. And then you let the scalar go to 0. Now, when you do that, then it doesn't matter if you write the differential on the left or you write it on the right. Because after the three-vector has gone to 0, then that differential element will commute with any quaternion. And effectively, this ends up being a directional derivative, but it's not really formally, because it's really this two-limit sort of process. Now, if we put our physicist hat on and look at this, then this definition applies to sets of light-like events in space-time. And for those light-like events, then the change in the three-vector part, the change in r, dr, will be less than the change in time. And I believe this is the domain of classical physics. So this is where events can be ordered in time. A happens, then B happens, then C happens. And this is what we're mostly comfortable with because this is our day-to-day life. Now this raises a question. What happens if those limits are reversed? Well, in that case, then all we can know is the norm of this derivative. Because if we let that scalar go to 0 first, then we've got that pesky three-vector, and writing it on the left is different than writing it on the right, except that the norms of writing it on the left is exactly the same as the norm of writing it on the right. So if we put our physicist hat on, this is going to apply to sets of space-like events where the changes in space are larger than the changes in time. Now this means that for that set of events, one event cannot influence another. They are independent of each other in terms of their causality. That doesn't mean we can't do any calculus on them, but it does put a constraint on the kind of calculus we can do. The most we can do is calculate the norm. And I believe this is the domain of quantum mechanics. So what Einstein was so troubled by was the underlying cause for the difference in the math between classical and quantum physics. And I believe it is because if you get the definition of what calculus is in space-time, in other words, how do things change when you have a mathematical unity of space and time? If you do that correctly, then in one case you'll have a directional derivative along the real axis and everything will be ordered in time in the standard kind of classical view. But if you now change the order of that, then the most you can know is the norm of the change, and that's, to me, is the fundamental difference between classical and quantum mechanics. So a deep math problem for people who work with quaternions is what picture actually goes with all this pretty darn abstract math. So we turn to René Descartes, who developed pictures of math using analytical geometry. We have this polynomial expression, and that's pretty abstract, but it helps to generate a picture that has precisely the same information, but since we are so visual, we can kind of get a handle on what it means much more quickly. So the solution to this riddle is to develop analytical animations using quaternions. So we make many events, 1,000, 3,000 events, either randomly or in a straight line. And then we do some math on that collection of events, either take the sine of it or take a polynomial sort of function. We sort it now by time, the results of doing that operation, and then we animate it using 3D software. So this will give you a sense of what we actually do. We write out something like Q random n and say, give me 10 of those sorts of things. Or I use actually constant linear motion even more often. Give me 10 things from -3, -3, -3 to 2, 2, 2. And then I have a whole bunch of commands out there that I've written, and we can pipe these together. So I take this constant linear motion and I put it into a Q hyperbolic cosine. I then take those results and order it in time, and then I take this whole command and I use a program called Q graph, and it's going to make a series of stills for the hyperbolic cosine ordered in time and then printed out in space. So we're going to start simple with inertial motion. And you can see that point just kind of moving in a totally straight line. What I found out was when I did this just as an animation, I couldn't really understand it, particularly when things got more complicated. I had to surround it with all these other images. I've got 3 complex planes over on the left-hand side. I've got a ty that shows how high it goes. I've got a tz, how far back it's going, and an xt that shows that it's moving to the left. I also found it useful to take every image that was there and superimpose them. That shows you all the states that are there, and then to kind of average all those states and show you one at a time, kind of picked out at random. I actually think the right-hand side is how we can visualize quantum mechanics. The wave function, which is supposed to represent every state, is what would be the all states kind of image, and then when you go and make an actual measurement, you get this collapse kind of idea where you get one of those data points and it kind of adds into the average. What's most impressive about this to me, though, is how simple the math is. The simplest math I can imagine doing is starting out with one quaternion and this keep on adding another quaternion to that first quaternion. And if you do that sort of thing, then you get this inertial observer, which is at the center of special relativity. So now let's look at the symmetry of electromagnetism, which is the group U1. We already know that that is a unit circle in a complex plane. And what we're just seeing that here as an animation. Now we have 3 complex planes, so it's kind of tilted relative to those, so these are 3 ellipses. But you could imagine it being a perfect circle in one of these complex planes and then being a straight line in the other 2. I really like the all states image, which shows that it's a totally straight line in space. and that's because this circle is about time's relationship to space, which means its velocity. So it flies apart very quickly, it gets to the maximum separation, slows way down, reverses direction, picks up speed, and smashes. Again, the algebra here is very simple. We just pick an arbitrary quaternion, we normalize it to itself, and then take n powers of it, and we get this nice simple animation. Now we can see the symmetry of the weak force. This is the group SU2, which is just, we take an exponential of a quaternion and we subtract its conjugate, and we get this kind of result. And I just took about 50,000 random quaternions and did this operation, and this is what it looks like. So it doesn't like the past, and then it shows up in about 8 different points, which you can see in the shadow actually, forms a circle and a sphere that shrinks into nothing. And I finally come to terms to why does it look like this. It looks like this because if you think of the Taylor series of an exponential with a like really small other terms, then it basically is 1, 0, 0, 0. And what that would be, if you thought about it on the complex plane, is just a dot out at t equals 1, and then x, y, z, and t being 0. Now, as the x, y, and z kind of expand on that point, this is kind of what it does. It forms this sphere, and the sphere hits a limit, and it kind of, it's a fight between the contributions of time and the contributions of space. But I think that might explain at least why it happens to look like this. I know that if you change kind of the proportions of the 3 vector, if you make them bigger or smaller, it has an effect. All right, well, anyway, let's move on. So now we've got the symmetries of the electroweak force, which we get basically by combining the results of the previous two, the normal quaternion normalized to itself times this exponential, and U1 is supposed to be an abelian group, which means it should be the same if I write it on the other side, and it does do this in this case because we're kind of using the same quaternion throughout the calculation. So this is likes the past now because it's kind of this product of U1 and SU2, and it just kind of avoids the future. But other than that, it forms a nice sphere out of it. And I'm all right. Well, let's move on. Now we can see the symmetry of the strong force, and we've got this nice uniform sphere. Algebraically, it's basically one of these quaternions, U1 cross SU2 quaternions, conjugated and multiplied by another one. And this is not the standard model, which is U1 cross SU2 cross SU3. As a matter of fact, I disagree with that model as being the most faithful representation of nature. The reason is that if you accept the standard model as it's kind of written there, U1, SU2, and SU3 should all be kind of complete equals in how they behave with each other, because they're just tensor products, and there's nothing special about one's relationship to the other. And yet that's not what we see in nature. Specifically, we see the symmetry U1 cross SU2, but we don't see U1 cross SU3. We don't see a weak strong symmetry. U1 is particularly close to the weak force. Now, why is that? There'd be no reason if the standard model was the kind of correct way to view these things. But there's another issue, and that is that SU3, the strong force, has something called confinement, where you don't get to see an isolated quark. And somebody won a Nobel Prize for that one, but they didn't explain why there was confinement for SU3 and not confinement for, say, U1. Certainly, if there was confinement for U1, the universe wouldn't be the way it is. But why mathematically it should be different when they're all the same sort of tensor product is not explained. Here we have kind of a visual justification for it, in that U1 and SU2 really are closer together because they are part of kind of one quaternion. And then we can't get SU3, the symmetry, unless we've got another U1, SU2 around. It just literally isn't defined unless you have two of these. And you just can't have one around. So it at least is suggestive of why these symmetries kind of go together. And I think actually why they have to be these three, because if you were an observer at 0, 0, 0, 0, and you see an event, then it will be on the surface of this sphere. And you just say that's one away, with some bit of x, some bit of y, some bit of t, some bit of time, and I'll just scale everything so it's somewhere on this particular surface. And then you'll say this has to do with one of those three forces, electromagnetism, the weak force, or the strong force. But there is another fourth force. There is gravity. And this is kind of a visualization of what how gravity might work with a standard model. And that is that if you're in a different location in the manifold, you measure what 1 is, and it's 1 to you. And someone at that other location on the manifold measures 1, and it's 1. What 1 is 1 to them. But if you do a smooth, continuous transformation from one spot in the manifold to another spot, you'll be able to see that what 1 is actually changes. And that underlying symmetry is known as diff M, the diffeomorphisms of the manifold. And basically it's kind of like saying there's a mass over on the right-hand side that's making the blue's idea of 1 be a little bit smaller than the yellow one's idea of 1. But now you've got all the four groups that have to deal with forces in nature. You've got U1 for light, you've got SU2 for the weak force, you've got SU3 for the confined strong force, and you have diff M for a metric approach to gravity. So that'd be neat if we just say, hey, look at this picture, and you should be able to spot the four forces of nature. So this third math widget that has to do with physics, I had to give you a little bit of background on two very important theories in physics. Now, general relativity is a great theory, but Maxwell's theory for electromagnetism is both better and has been shown to be extendable. So general relativity is a beautiful minimalist theory. All efforts to add a little bit to general relativity to date have failed. An example is when somebody tried to put in a background metric that was fixed and looked at the consequences of that. One of the consequences of that was that there should be a dipole moment for gravity waves, because if you have something wobbling all by itself, it could put some of the energy into the background metric, and that gives it a chance to be a dipole. And yet we've got experimental data that says there are no that the lowest mode of emission's got to be a quadrupole, and that's a huge constraint that on doing alternatives. And of course, there's the problem that quantization efforts have failed. I mean, we realized in 1930 that we needed to quantize the approach to gravity, and they have meetings from time to time, and there are people who work on this full time, and they're very bright, and they have all failed. And to me, that should be kind of a message that maybe we shouldn't try to quantize it because it can't be done. That's like that kind of simple logic somehow doesn't catch on. It's a little too threatening. Maxwell's equations, on the other hand, actually improves with additions. It started with Maxwell himself, who added on the ampere current because it would make the equations look kind of better. These equations had Lorentz symmetry built into them, and Einstein's kind of observations of the EM laws actually led to special relativity. Quantization works fine. You usually had to pick a gauge, and then, but really a lot of the basics of quantizations were worked out with electromagnetism. And in more modern times, when we had to come up with theories to explain the weak force and the strong force, what we did was we took the gauge kind of group of EM, which is U1, and said, now let's put in this SU2, let's put in this SU3, and let's build theories out of that, and that actually did work. So let us write the Maxwell field strength tensor in the normal way, but also as a quaternion. So the tensor expression is an anti-symmetric rank 2 field strength tensor that's spin 1, because if you change the indices, it will flip signs, and that's a property of spin 1 field. And there they all are, zeros down the diagonal. Those zeros are important because they indicate why this theory is invariant under a gauge transformation. So if we want to form an equivalent expression out of quaternions, what we do is we just have the 4 derivative of 4 potential, subtract away the conjugate to get rid of the scalar term, which is where all the gauge stuff goes, and there you have it. There's an E field and a B field. Now I want to extend the notion of a field strength tensor by using a symmetric tensor. It's rank 2, and I think it will be a place where a spin 2 field can live, and spin 2 fields indicate that you have like charges attracting, so it's kind of already implying that maybe this might deal with gravity. So if we just write out what the symmetric product is, you'll notice that I'm now including this capital gamma, which is the Christoffel symbol of the second kind, and it's necessary because we're adding these two together, and those connections kind of must be included. Now, a connection under certain technical conditions is how a metric changes. And so that's interesting, because if we now take derivatives of these fields, we'll have the second order derivative of a metric, and that means we might be able to come up with a constraint on what metrics can be, as a second order differential equation. All right, so we've got this E field, and if you know what the standard E field is, this is very similar. It's just got one sign that's different. The sign of the gradient of phi is that's different. And then we've got this small B field, and it's similar to cross product, except that the signs are the same. So this feels much more symmetric, and indeed it is. And then we've got this G field, which is basically all the terms along the diagonal. So now we want to write that symmetric tensor using quaternions, just like we did the antisymmetric tensor using quaternions. But that's a real problem because, particularly for that nice symmetric B field, a tensor doesn't want to do that. And so the solution, I like to call this the California solution, is to make everything positive, and then multiplication commutes, because, you know, how could there be a minus sign in there when there's just no minus signs? But another problem that immediately pops up is you say, well, but it's no longer a division algebra. Well, since I've kind of made this as a matrix representation, I can ask some software to invert this matrix, and it can. It does so, and then it says, you know, and I'm going to have to divide by this particular number. And you say, okay, well, what is that number? I just have to make sure that number is never 0. And that number is never 0 if you take the eigenvalues of this matrix and you say we cannot use the eigenvalues in this matrix, and then it's a fine division algebra. It's kind of funny that here I am at this Clifford Algebra conference, and what I have here is in fact not a Clifford algebra, because it's these things, the wedge kind of thing ends up being, you know, summing, not the difference of those two. And in fact, this is like, this has been invented before by a fellow named Clyde Davers. He calls them hyper-complex numbers. I don't see anything hyper about these. I don't see anything complex about these. These are like the simplest things out there. It's just put them in a matrix and go. So we have difference in what we call them, but you know, they end up doing the same thing. So now that I've got my, I actually call that the even representation of quaternions. But I can now represent a symmetric field tensor this way, and it's kind of the first steps towards a gravity theory. So again, I do the subtraction step, and so there's no gauge. It's invariant under gauge transformation. And what I have shown is that if you can take this what I call the exponential metric, which is also known in the literature as the Rosen metric, and it actually solves the first field equations, which I call general Gauss's equation, which is written right there. Since it's static and it's diagonal, it allows a bunch of terms to kind of drop out, and basically the exponentials nicely also bow out, and you just basically end up with this kind of an expression that even Poisson would recognize, coming out of the metric itself, which is really either incredible luck or it's an indication that we're onto something very deep. So another issue that we have to think about very carefully, or we will be cut up by the critics, it has to do with the spin coupling term. And we need to generalize this so that we can see both spin 1 symmetry for where like charges repel as they do in EM, and where like charges attract as they do in gravity, and that requires a spin 2 field. So if we just take a current coupling term like this, and we form the product of these two, then the scalar that we get there goes into the action of the proposal. And since these are quaternions, we have a phase, and we can think about how these different parts of the parts transform. Specifically, if J and J prime happen to be pointing in almost the same direction, then in the case of the stuff in pink, those guys really kind of add up, and they will basically throw in a factor of 2, and it will only take pi rotations to kind of get back to where it started. And that's a characteristic of a spin 2 field. And then if we think about the other terms where they're actually fighting each other a little bit, it's going to take them 2 pi rotations to get back to go. That's a characteristic of a spin 1 field. Now I didn't show it, but you can repeat this calculation with the even representation where you have J2 and J2 prime coming together, and then it's really neat. The parallel current actually has spin 1 symmetry, and the perpendicular component has spin 2 symmetry. Very much a calculation you should do. It's a fun little one. And if you want more information about this particular proposal, then just search for Gem Action on YouTube, and there's about a 22-minute talk that I go into kind of details about how to derive the field equations and that sort of thing. So new math should feel uncomfortable. I mean, figuring out the difference between classical and quantum mechanics, claiming that that has nothing to do with anything other than math, is certainly kind of a new position to take. There are books and conferences on the Copenhagen interpretation or the many worlds approach, and people passionately believe in their own reason for the difference, or the belief that you cannot understand the difference, I just don't see any way of like winning over those people. In some ways, I don't care about winning over those people. It's more that the more I think about this, the more comfortable I am with this division. I'm really at peace with it, and I don't know how we're going to sell it, but I also don't care very much. But that's the kind of battle that might go on in the future. Do we finally have a really a kind of explanation that would actually make Einstein happy because it was just logically clean as far as the difference between classical and quantum physics? And I think it is. Now these animations, they really are odd. And I like to say if you've got an important function very well defined, I'll go ahead and make the animation myself, or you can go to quaternions.sourceforge.net and download the software yourself and do it. But here's a picture of a cosine function, and this really bothers me because I expected to see, the typical kind of humps, and it doesn't look anything like that. I mean, why is it so straight in the all states view? And it's so straight because we keep on feeding the same quaternion that points in the same direction into this sort of thing, and we can see these things coming together and flying apart, and in some ways I feel lost about it, but that's too bad for me. It's the way the math is working, and I just have to kind of wrap my head around it, and it's not easy to do so. And then finally, the third issue we got to had to do with the commuting properties of 4D division algebras, and we got that representation of what quaternion was from Hamilton, and everybody since then has towed the line, and so it's like fundamental in how you view 4D division algebra. They don't commute. AB does not equal BA. It's that so many times you read that, so many times you read that, and to come up with something where, well, as long as you exclude those eigenvalues, you can have something where AB does equal BA. That really undercuts this thing that's been drummed in so many times. if you go and study quaternions. But of course, not only is that uncomfortable, but it's kind of fun because, at least for me, I like to look at my assumptions of what things are, and then precisely, if I can, find out another way of looking at the same thing. And I think that's really important because nature's the one who's systematically creative, and I believe she knows how to do both of these things. She knows how to do both gravity and electromagnetism in very small, compact theory. And the current trend is to make things super ridiculously complex. And to go the other direction, quite frankly, it's very hard to get anyone's attention. But then again, I don't, kind of like nature doesn't care whether we get it. I don't care if anybody gets what I get. I make an effort. And I think this is incredibly beautiful and elegant. And if you can listen in, great. And if you're too busy, hey, good luck with your own work. But I feel uncomfortable with this math. But that's my own problem. Nature looks comfortable with it. And in the end, that's what matters most. Thank you very much.